Welcome to this video on Rolle's theorem and the mean value theorem. Rolle's theorem says that if you have a function f that's continuous on the closed interval ab and differentiable on the open interval ab, and f of a and f of b are equal to 0, which means that f crosses the x-axis at a and b are roots of the function, then there's a point c where f prime of c is equal to 0. So that means that at c the tangent line is horizontal and the slope is 0. This is illustrated on the following graph. As you can see, a and b are roots of the function, and within a and b there are values of c where f prime of c is equal to 0. So as you can see, the theorem says that there exists a point where f prime of c is 0, but c may not be unique. So there might be multiple points where that's the case, or there may just be one point, but there's at least one point where the conclusion is going to hold. The mean value theorem is sort of a generalization of Rolle's theorem. So you have the same assumption on continuity and differentiability, but the conclusion is that there's a point c where f prime of c is f of b minus f of a over b minus a. So notice there are no assumptions here that f of a and f of b are equal to 0. So the function doesn't have to cross the x-axis at a and b. If you consider this expression, f of b minus f of a over b minus a, then this corresponds to the slope of the line going through a f of a and b f of b. That's because f of b minus f of a is the rise of this secant line and b minus a is the run. So rise over run gives you the slope of the secant line. So the conclusion is that there is a point c where the slope of the tangent line at c is equal to the slope of the secant line going through a f of a and b f of b. So as you can see, once again, there's at least one point c, but there could be multiple points. So in this graph, there are 3 values of c where the slope of this tangent line is the same as the slope of the secant line. That's because these tangent lines are parallel to this secant line. One more thing that could be said about the mean value theorem is that it is a generalization of Rolle's theorem. That's because if you assume now that f of a is equal to f of b, if you go back to the conclusion of the theorem, if f of b and f of a are equal, the numerator is equal to 0, and the conclusion is f prime of c equals 0, which was the conclusion of Rolle's theorem. The other thing is that we can use Rolle's theorem to prove the mean value theorem. This is something you will do in the exercises. The mean value theorem in its own is not that useful, but it is very useful to prove other theorems. For example, in the exercises, there's a hard exercise where you're asked to use the mean value theorem to prove a fundamental theorem of calculus, which is a very important theorem, probably the most important theorem in calculus there is, and you will see it more thoroughly next term in Cal 2. We now look at an application of Rolle's theorem when solving equations, more precisely when we want to know the number of solutions to a specific equation. So consider the problem of finding the solution of the equation f of x equals 0, where f is continuous and differentiable. So recall that if f of x equals 0 has 2 solutions, a and b, then by Rolle's theorem, f prime of x equals 0 has a solution, because there will be a value c between a and b where f prime of c will be equal to 0. The contraposition of the previous statement is that if f prime of x equals 0 has no solution, then it's not possible for f of x equals 0 to have 2 solutions ab. By that we mean 2 distinct solutions AB, and there must be at most one solution. So the idea is that whenever we have 2 roots of f, then we'll always have in between a root of f prime. So similarly, if f prime of x equals 0 has one solution, so there's no s there, one solution, there can be at most 2 solutions for f of x equals 0, because if there would be 3 solutions, we would have in between each pair of solution a solution for f prime of x equals 0, But since we only have one, then we cannot have three solutions for f of x equals 0. So we always have one less solution for f prime of x equals 0 to the number of solutions for f of x equals 0. So taking that to another level, if f prime of x has two solutions, then there can be at most three solutions for f of x equals 0, and so on. So the recipe to find the exact number of solutions of an equation f of x equals 0, even though that might be hard, is typically to use the intermediate value theorem to locate or to find an enclosing interval for each root of the function, and then we use Rolle's theorem to argue that they are no more than a certain number of solutions. So here's the following problem. Find how many solutions the equation x to the 5 plus 3x cubed plus x equals 2 has. So we first write the equation as f of x equals 0. So that gives us x to the 5 plus 3x cubed plus x minus 2 equals 0, where f is the function on the left-hand side. And then since it's a polynomial, we notice that it's continuous and differentiable. Therefore, we'll be able to apply Rolle's theorem to it if needed. Now we look at f prime of x, and we try to see how many solutions f prime of x equals 0 has. So in that case, f prime of x is 5x4 plus 9x squared plus 1. Now, the first two terms are non-negative, while the last term is positive. So overall, the function is always positive, and it will never be equal to 0. So this equation, f prime of x equals 0, has no solution. So recall from what we said before, if f prime of x has no solutions, it will not be possible for f of x equals 0 to have two solutions. So there will be at most one solution. Now, once we know that there's a certain number of solutions possible for f of x equals 0, we try to locate them. So this is where we might want to use the intermediate value theorem. But here we could also take a look at the function f. Notice that it's a polynomial. It's a polynomial with an odd degree. And since the coefficient in front of x to the 5 is 1, it's positive, we know that the behavior of the polynomial as x goes to infinity and minus infinity. As x goes to infinity, the polynomial goes to infinity. As x goes to minus infinity, the polynomial goes to minus infinity as well. That's due to the odd power of x for the leading term. So x to the 5 goes to infinity as x goes to infinity. It goes to minus infinity as x goes to minus infinity. And since that term, x to the 5, dominates every other term in the polynomial, it dictates the behavior of the polynomial to infinity and minus infinity. So we know that because the function goes to infinity and minus infinity at both ends, and it's continuous, it will cross at some point the x-axis. But then we can be more precise with the intermediate value theorem and try to locate where the root might be. Now, if we just take some random number, 0, f of 0 is minus 2, which is negative. So if we can find a point where the function value is positive, then by the intermediate value theorem, the interval starting at 0, ending at that other value, will contain or will enclose a root of f. So if we look at f of 1, for example, it's equal to 3 and it's positive. So between 0 and 1, there is definitely a root or a solution to f of x equals 0. Overall, we know that there's a solution and there's at most one solution. So finally, we can say that the equation has a unique solution and it's in the interval 0, 1. Thanks for watching.